Good morning, chemical engineering students. I'm going to show you something kind of cool today. How to use Excel to design a distillation column using the Lewis method when it's not an ideal solution, like the ethanol water system. This requires activity coefficients, which require then knowledge of the liquid phase composition. But if you're trying to calculate the liquid phase composition, you can't calculate the activity coefficients. It's sort of a circular reference that Excel will not allow us to do. So I'm going to show you how this is done.
Let's look at the way I normally calculate the flow rates and compositions for a distillation column using the Lewis method on an ideal mixture. So we normally know the liquid flow rate from the distillate flow rate and the reflux ratio. So we could calculate that. The composition of that liquid has to be the same as the distillate composition, so we know that. There's no vapor coming out of the total condenser, so those are blank. The temperature can be determined from the bubble point equation because we know that the K values here are functions of just the temperature. The bubble point equation is a function of the temperature and the liquid phase composition, which we know. So the temperature now can be calculated along with the K values by iterating the temperature to satisfy the bubble point equation. For the next stage, 1, we can calculate the vapor flow rate as just the sum of the liquid leaving the total condenser and the distillate. So that can be calculated. The Y value has to be the same as the X value leaving the total condenser or the distillate composition. So we know that. The liquid flow rate can be determined from an overall material balance. So we can calculate that. In fact, the liquid flow rate all the way down the column can be calculated with an overall material balance, and at the feed stage, it's increased, assuming a bubble point liquid feed. The vapor flow rate at each stage can be calculated just using the equal molal overflow assumption. So these are all calculated, so we won't worry about those. Now, once we know the vapor composition in stage 1, then we can calculate the temperature, because we can use the dew point equation, which is a function of the temperature, and Y, which we now know for stage 1. So temperature, and along with the K values, can be calculated by iterating the temperature to satisfy the dew point equation. Now, the X value for stage 1 can be calculated using equilibrium relationship y equals kx, because we know both y and k, so that we can calculate that. The next stage, we can't calculate y using a mole balance around stage 2 because we don't know the composition of the liquid in stage 2. We don't know the composition of the vapor coming into stage 2, so there's too much we don't know in order to calculate the Y value for stage 2. But we can do a benzene material balance around stage 1. See, for stage 1, the material coming into stage 1 is from the liquid leaving the total condenser and the vapor leaving stage 2. What leaves stage 1 is L at stage 1 and vapor at stage 1. So the only thing we don't know in all these variables is the value of Y leaving stage 2 and going into stage 1. That's what we need to calculate. And so we know we can calculate that using a mole balance around the stage above it. And Then we can calculate the temperature using the dew point equation. And finally, we can calculate x using the equilibrium relationship y equals kx. And we proceed that way down the column using a mole balance around the stage above it to get the y values. Now we run into a problem for non-ideal mixtures if we use a activity coefficient model like the Wilson equation, where the k values are no longer just functions of temperature. They're functions of temperature and the x value. So that's a problem, because if we're trying to calculate the composition in the liquid phase, we need that very same composition in order to calculate the k values. So Excel calls this a circular reference, and it will not do that. So we have to have a different strategy. And my strategy that I use is to start at the bottom. So let's start at the bottom of the column. If you know the distillate flow rate and the reflux ratio and the distillate composition, or some combination of those, you can calculate the bottom's flow and its composition using an overall mole balance around the whole column. So we can calculate these. And as before, a combination of overall mole balances and the equal mole overflow assumption allows us to calculate all the liquid and vapor flow rates. The temperature can be calculated using the bubble point equation, which is a function of the temperature and the liquid phase composition because of the activity coefficient. But we know x, so we can calculate the temperature and the k values and iterate the temperature to satisfy the bubble point equation. Then y can be calculated using the equilibrium equation, y equals kx, and so we can calculate that. We can calculate the liquid phase composition leaving stage 10 and going into the partial reboiler using a mole balance around the stage below it, or the partial reboiler. The only stream coming into the partial reboiler is the liquid coming from stage 10, and the streams leaving the partial reboiler are the bottom's flow rate and the boil up. That leaves only one unknown in this mole balance equation, and that is the liquid phase composition coming out of stage 10. So we can now calculate this. Again, we can use the bubble point equation to calculate the temperature by iterating the bubble point equation and the temperature, because we know the liquid phase composition for the activity coefficient, and the temperature will be guessed. So we can calculate then the vapor composition leaving stage 10. And we can do these calculations on up the column, each time calculating the liquid phase composition using a material balance around the stage below. And at the very end, we can compare the composition that we calculate for the distillate and compare that to the composition that we started with. That's why I have a delta down here. So since Excel calculates functions from top to bottom, left to right, how do we get it to calculate starting at the bottom of the column and work its way up? Well, we'll have to write a little Excel macro, and that's a Visual Basic program. It's really in the background of all these calculations, and I'm going to show you how to do it. It's not really very hard. We start by clicking View And then we'll have a symbol here for macros, and click that, and we have the option of viewing macros or recording macros. And we won't get into this. So if you click record macro, this screen pops up, and you can give it a name and a shortcut key. In the example I'm going to show you, I actually call this bubble, and the shortcut is Control-Shift-B. Then we click OK, and everything after that we do will be recorded in the background in Visual Basic code that we can actually look at. So now we're going to use the goal seek function to make the bubble point or dew point equal to 0 by changing the temperature. And so we go to Data, and then we press What If Analysis, and then Goal Seek. Excel is listening to all that and recording it as this code in Visual Basic. So in Goal Seek, you select a cell and force it to be 0 by changing another cell. So we choose a bubble point function and then change the temperature until it's 0. I actually started with this cell here and made it 0 by changing this temperature. Once we've done that, just for that one cell, we stop the recording by going back to View and hit Macro, and you'll see a stop record, and stop that, and then we'll go in and edit that. So now I go into the View macro and see this bubble macro. I click on that, and here's the code. And this is just a subroutine, so that's automatically put there. All this is automatic. The bubble is the macro. The keyboard shortcut is Control-Shift-B. And then there's this kind of garbage in here, which I think refers to my moving around to select what if analysis, etc. It's not necessary, and we'll cut that out. And then here's the function for goal seek. Let's clean this up a little bit. So here I've cleaned it up. And so I just have the identification. These are comment symbols, and so this is not an actionable function here. It's just identifying this. But here we have the range Q7, which was the bubble point criteria. Goal seek, goal equals 0. So we wanted to make it equal to 0 by changing the cell range K7, and this was the temperature. That's just the language for Visual Basic. I didn't know how to do that. It just records that automatically. But now we can edit this so that it will automatically do the same goal seek function all the way down from the total condenser down to the partial reboiler. So here is the edited macro. And you don't necessarily have to understand exactly what's going on here. Just go in and edit exactly like this, and it will work. So we say for I, which is just an integer, but it represents the row, 18, and row 18 is the partial reboiler, to 7, which is the total condenser. We're going to do something, and we're going to step it each step by -1. So it'll go from 18 to 17 to 16 on to 7. And each time we do this function here, which is the goal seek function, it says next I, and then we go to the next one. So we changed the statement that originally looked kind of like this down here to cells I, which is the row. It starts off with 18, and Q, which is the column. And we goal seek that to be 0 by changing cell, cells, and this tells you what cell to look at. And this is row I, and K is the temperature. So it's going to go through and change the temperature until this cell is equal to 0. Once it's done that, it goes on to the next row. And this is repeated until it gets to 7, and then it stops. After this, I have one more thing to do. I say that the range, this looks more like the original thing that was recorded by the macro. I say range Q19, which is a cell that has the guessed distillate composition compared to the stage by stage distillate composition. And you can see that if you look at the spreadsheet. We make that equal to 0 by changing the guessed distillate composition. And that's the end of the subroutine. And then that's what happens when we press Control-Shift-B here. So here is the spreadsheet initially. I have guessed a distillate composition of 0.8, and I have guessed temperatures. It's important to put something in here reasonable, and I put all temperatures being 80 and then 90 at the very bottom. And then all these other cells are all calculations based on those. Now I'll move on over here to the right side of the spreadsheet. And when I run Control-Shift-B, it will look at this value here, because it starts at the bottom. And I've already calculated the X values from the overall material balance. And so it will then iterate by changing the temperature here until the bubble point is 0. And it'll keep doing that up and up the column. So here's what it looks like after the first iteration. Let's zoom in here. The bubble points were all set equal to 0 by changing the temperatures. But then the very last statement said, take a look at the guessed distillate composition and compare that to the distillate composition, or in other words, the liquid composition leaving the total condenser, and compare them and change the distillate composition until this value is 0. Well, that kind of messed up all of these. And so we're going to have to run this macro several times in order to get the final answer. And so what I do is I just press Control-Shift-B a number of times, maybe 10 times, it only takes a second, and until I no longer see any changes occurring in the temperatures or the compositions or the bubble points. Let me show you the final result now. So here is the final result. Let me zoom in here. All the bubble points are now effectively 0. They're not going to be exactly 0, but they're close, pretty close. And this will be the temperature profile in the column. I can move over now to the distillate composition, and you can see that it has settled now on a distillate of 0.823 mole fraction. Actually, this is ethanol and not benzene. So starting with a guess for the distillate composition and the distillate flow rate, we can calculate using an overall process mole balance, the liquid flow rate, this would be the bottom's flow rate and its composition. We also have the feed in that calculation. So those are calculated based on the overall mole balance of the process. Then, starting at this stage, we calculate the liquid flow rate using an overall mole balance for the stage, and we calculate the vapor flow rate using the equal mole overflow assumption. We calculate the liquid phase composition using a mole balance of ethanol around the stage below it, if you remember that. and then the y value is calculated using equilibrium relationship. And we work our way up the column, and then at the end here, we calculate the vapor phase composition going into the total condenser and set this value here equal to that. So this is calculated by stage calculation. And then this is compared in that delta cell to the distillate composition. And when they're the same, then we have our solution. One of the nice things about an Excel simulation, of course, is that every time I change the operating conditions, it redraws the McCabe-Thiele diagram, or those stair-stepping, and you can see here that everything looks fine, looks correct. The values at the bottom are going to the bottom operating line. The values at the top are going to the top operating line. Everything that is leaving each stage is hitting the equilibrium line. You do notice here, though, that at this stage, which is, let's see, this is the partial reboiler, that's stage 10, so this is stage 9. It would be better if it dropped down here to the top operating line rather than going to the bottom operating line. You get a little bit better separation that way. So I would instead feed to stage 10 rather than stage 9, so this can go down to the top operating line and not go down to the bottom operating line until stage 10. Well, I hope this has been of some value to you, and you now know how to program a little bit in Excel's Visual Basic.